When we reflect a hyperbola, it is tempting to focus entirely on the curved lines bending across the plane, but capturing the math accurately requires tracking the graph's invisible framework, its asymptotes and specific reference points. As the curves flip, those structural anchors dictate exactly where the graph lands. This provided graph shows the specific baseline hyperbola we will use to trace these shifts. By reading the graph, we can extract our working parameters. The vertical asymptote gives us a p-value of 1, and the horizontal asymptote gives us a q-value of 2. We also have a clear reference point to track at p23. This allows us to establish our working baseline equation, f of x equals 1 over x minus 1 plus 2. Those asymptotes define the absolute limits of this graph. Because the curve can never touch them, our domain is restricted so x cannot equal 1, and our range is restricted so y cannot equal 2. These limits and parameters form our baseline anchor. As we apply algebraic reflections, we are actually calculating the precise mathematical movement of these anchors. The rule for an x-axis reflection dictates that y equals negative f of x. Visually, the entire curve flips downward across the axis. If we track our specific reference point, p2, 3, mirrors directly down to become p', 2, negative 3. To match this geometric drop algebraically, we negate the entire baseline equation. This step introduces a common error. You must distribute the negative sign to the horizontal asymptote term at the end as well. Doing so yields our reflected equation, h of x equals negative 1 over x minus 1 minus 2. The algebraic negation of that plus q term drops the horizontal asymptote from y equals 2 down to y equals negative 2. This inherently changes the function's range, while the domain remains completely intact. A y-axis reflection operates under the rule y equals f of negative x. This creates a lateral shift. Our original point at p2, 3 now travels horizontally, mirroring across the y-axis to land at p', negative 2, 3. Let's test the algebra on this lateral shift. Try mentally substituting negative x into our baseline equation. What does the new vertical asymptote become? The initial substitution gives us 1 over negative x minus 1 plus 2. Leaving the denominator in this state obscures the actual shift and often leads to graphing errors later. The fixed is to factor out the negative sign from the denominator. This clarifies the true parameters, simplifying the equation to negative 1 over x plus 1 plus 2. This algebraic adjustment proves why the vertical asymptote physically shifted. The denominator went from x minus 1 to x plus 1, moving our vertical barrier from x equals 1 to x equals negative 1. The domain is altered, but the original range is preserved. There is a third type of reflection, flipping the graph over its own intersecting asymptotes. The branches swap diagonally into the opposite quadrants, moving our reference point from p23 over to p', 0, 1. The algebraic rule for this internal flip is highly specific. Only the sign of the numerator, the k-value, changes. The rest of the equation is untouched. Because only the numerator changes, the asymptote reflection alters the trajectory of the curves, but leaves the entire geometric skeleton, the domain, range, and asymptotes, completely locked in their original positions. Viewing the three reflections side by side reveals how distinctly they manipulate the same baseline curve. Each reflection targets a specific piece of the formula. The x-axis reflection alters the outside variable q, impacting the range. The y-axis reflection alters the inside variable p, impacting the domain. The asymptote reflection alters only the top variable k. This table maps the standard baseline equation against the three algebraic transformation rules and their resulting asymptotes. Graphing hyperbolas effectively requires translating visual flips into algebraic adjustments. By applying these specific mathematical rules to the asymptotes and reference points, you can accurately construct the new graph every time.